Consider this explainer your ultimate briefing, a real masterclass for you junior performance engineers on what it actually takes to ride the ragged edge of engine performance. Today, we're tackling the single greatest limiting factor in gasoline engine engineering. It's this invisible wall that completely dictates how much power we can make, how efficient we can be, and most importantly, how long our engines are going to survive.
So what exactly is this core enemy? Well, we call it end gas autoignition. Now, in a perfect world, right, combustion starts right at the spark plug and burns nice and smoothly across the cylinder. But while that flame is traveling, all the unburned air and fuel ahead of it, what we call the end gas, is getting fiercely compressed and heated. If that pocket gets too hot before the flame front actually gets there to burn it normally, boom, it spontaneously ignites on its own. And guys, this isn't just some harmless secondary fire. It's a violent, uncontrolled chemical chain reaction. It creates these supersonic pressure waves that can literally destroy engine components from the inside out. Here's our game plan for today's session, so you know exactly how we're going to systematically conquer this. We'll cover the anatomy of autoignition, identifying knock and LSPI, thermodynamics and octane, sensing piezo versus ion, mitigation strategies, and finally, ECU calibration tactics.
All right, let's dive right into Section 1, the anatomy of autoignition. Let's look at the micro-level chemistry here.
So contrary to what you might think, autoignition doesn't just happen instantly. It's actually a very precise two-stage oxidation process. Stage 1 is low-temperature oxidation, between 250 and 550 degrees Celsius, where the fuel reacts with oxygen to form radicals. Then, as temps rise between 550 and 750 degrees, we hit Stage 2, the NTC, or negative temperature coefficient region. Now this is super interesting, because here, the chemical reaction actually slows down. It gives us this brief critical resistance window where we can fight back. But if we blow past that and temperatures cross 800 degrees, that's Stage 3, hot ignition, total thermal runaway, game over.
50 bar per millisecond. That is how fast the pressure can spike during that severe Stage 3 hot ignition. To really put that into perspective for you, a normal, healthy combustion raises pressure by just 1 to 4 bar per crank angle degree. Hitting 50 bar per millisecond means the mixture is igniting almost instantly across a massive volume, instead of acting like a smooth propagating flame. We are talking about sheer, unadulterated violence inside the cylinder. Moving right along to Section 2, identifying knock and LSPI. We're transitioning to the field now. Look, if you want to be a calibrator, you have to train your ears. You've got to know how to identify these events accurately, because not every noise is autoignition. Standard knock, that's a high-pitched metallic ping or a ticking sound, usually sitting around 6 to 12 kilohertz. Now, if you hear a lower frequency thump, say 1 to 2 kilohertz, that mostly shows up on cold starts and fades as the block warms up. Well, that's just piston slap. And if the sound is totally rhythmic and synced to the cams, that's your valve train. Seriously, knowing the difference right off the bat will save you hours of chasing ghosts on the dyno.
But we also really need to contrast your standard spark-initiated knock with its terrifying bigger brother, low-speed pre-ignition, or LSPI. You'll often hear it called super knock. Standard knock happens after the spark plug fires, right? LSPI happens before. It is a completely catastrophic event, and it's notoriously common in modern small-displacement turbocharged engines. It's usually triggered by these rogue little oil fuel droplets that scrape past the piston rings. Under heavy boost and low RPMs, they auto-ignite and set off this massive pre-ignition event.
Let's put some hard numbers to that destruction. Normal combustion, safe, smooth, 1 to 4 bar per degree. Medium knock bumps that to 10 to 20 bar, which, will slowly erode piston crowns and crack ringlands over time. But LSPI, that spikes at over 100 bar per crank angle degree. No joke, a single LSPI event can literally shatter a forged connecting rod or blow a hole straight through a piston in a fraction of a second. It is immediate failure.
All right, Section 3, thermodynamics and octane chemistry.
Now let's look at the thermodynamic triggers, because there's this really fascinating contrast in engine design here. Engine knock, as we know, is rogue, destructive, uncontrolled autoignition. But engineers have also created HCCI, homogeneous charge compression ignition. And HCCI deliberately induces autoignition everywhere in the cylinder, all at the exact same time. When it's controlled perfectly, it gives you diesel-like efficiency, but with gasoline-like emissions. So the difference between completely trashing an engine and achieving peak thermal efficiency is literally just about who is in control of the autoignition. As calibrators, your absolute best shield in this fight is your fuel chemistry. Think about it.
Higher compression ratios squeeze the air harder, which aggressively raises those end gas temperatures. Standard pump gas, that's going to auto-ignite as low as 246 degrees Celsius. But ethanol? Ethanol holds out all the way to 365 degrees. So using these high-latent heat fuels massively widens your thermal margin before that end gas reaches its breaking point.
Moving into Section 4, Sensing. We're looking at piezoelectric versus ion.
You simply cannot tune what you cannot accurately measure, right? So how does the ECU actually know the engine is knocking? Traditionally, we bolt these piezoelectric sensors right to the block. They're basically just industrial microphones hunting for those 5 to 20 kilohertz vibration signatures. But there is a much more advanced way to do it: ion current sensing. Instead of just listening for vibrations ringing through a chunk of metal, this system uses the spark plug electrodes themselves to measure the electrical ionization of the combustion gas directly inside the cylinder. It gives us crazy microsecond accuracy, totally bypassing all that mechanical background noise.
Okay, Section 5, Mitigation and Cooling Strategies. When you're building a calibration, you need to know how to cool the charge so you can push those performance limits safely. Here's your core mitigation arsenal. You can retard the ignition timing, upgrade the intercoolers, run water methanol injection, dump in extra fuel for cooling, or use cooled EGR. But, and this is absolutely crucial to understand, every single choice here is a strict trade-off. Retarding timing stops knock, for sure, but you lose power. Dumping extra fuel cools the cylinder, but you completely tank your fuel economy and emissions. Your entire job is balancing that maximum engine torque against making sure the components actually survive. Let's zoom in on one of the most potent tools we have for high-boost applications: water methanol injection, or WMI. This is just an incredible chemical cooling method. The water vaporizes and aggressively yanks heat right out of the intake charge. We're talking dropping temps by 30 to 60 degrees, while the high-octane methanol steps in as a fuel supplement. This setup literally lets you safely advance your ignition timing by 4 to 8 degrees, pushing you right to the very edge of maximum power without blowing the engine to pieces. And that brings us to Section 6, Modern ECU Calibration Tactics. Let's look inside the brain of the engine. So how do we actually fight this battle dynamically? Well, on the dyno, we build 3D timing maps. Every single cell in this map corresponds to a specific RPM and a specific engine load, and it holds a target spark advance number. Basically, we're trying to safely surf this razor-thin line just below MBT, maximum brake torque. You want that spark to fire as early as physically possible to make power, but late enough to guarantee the flame front completely consumes the end gas before it has a chance to auto-ignite. But engines aren't perfect, so let's look at the active defense system. When the ECU detects a knock event on a specific cylinder, it reacts asymmetrically. Step 1, it detects the knock. Step 2, it retards the timing extremely rapidly, pulling 1 to 3 degrees immediately on the very next cycle to protect the hardware. Then, Step 3, once the knock stops, it advances the timing back very, very slowly, maybe just 1/10 of a degree at a time, to claw back that lost power. So the mantra is, retard fast, advance slow. It perfectly protects the engine. Here's the thing though, reacting to knock still means the engine had to take a hit first. Enter predictive knock control. In highly advanced modern ECUs, the computer is constantly running virtual thermodynamic models of the cylinder in the background. It estimates the internal conditions and proactively pulls timing before the knock event even has a chance to physically happen. It's essentially seeing the future just to save your rod bearings. Pretty wild, right? So to summarize our core takeaway from this explainer, combustion is a literal race. It's a race between the controlled flame front and that unburned gas just waiting to explode. Every single decision you make widens or narrows the margin in that race. As the quote goes, every calibration decision is a negotiation with end gas auto-ignition. Mastering this is the core discipline of gasoline engineering. At the end of the day, you are the referee in that race. So I'll leave you with this final thought as you head out to the test cells today. Are you ready to balance maximum torque with component survival? The physics, well, they aren't going to change. But your mastery of these mechanics will entirely determine whether you build a champion engine or just a really expensive bucket of shrapnel. Get out there, trust your sensors, and never stop learning. We'll see you on the dyno.